There are 23 people in a room. What is the probability that at least 2 of them share a birthday? Your gut says it is tiny. 23 people, 365 days. That is less than 7% coverage. The chance should be almost 0. It is over 50%, not close to 50, not barely 50, 50.7%. And if you raise the number to just 70 people, the probability climbs past 99.9%. 70 people. Virtually guaranteed. This is the birthday paradox. It is not a paradox in the logical sense. Nothing contradicts itself. The math is airtight. It is a paradox of intuition. Your brain gives you an answer that feels obviously correct, and that answer is wildly, embarrassingly wrong. And the reason your intuition fails here is the same reason it fails across all of probability, finance, epidemiology, and cryptography. You are about to understand why. Let us start by computing the exact probability. Assume 365 days in a year. No leap years. Every birthday equally likely. None of these assumptions are perfectly true. Real birthdays cluster in September. Leap years add a day. But these simplifications make the math clean, and here is the beautiful part. Relaxing them only makes the paradox stronger. Non-uniform distributions increase collision rates. We want the probability that at least 2 people in a room of n share a birthday. Computing this directly is a nightmare. You would have to account for every possible combination of shared birthdays. Pairs, triples, clusters, it is a mess. So we use the complement. Instead of asking what is the probability that at least 2 people share a birthday, we ask what is the probability that nobody shares a birthday. Then we subtract from 1. The probability that all n people have distinct birthdays. Person 1 walks in. They can have any birthday. That is 365 out of 365. Probability 1. Person 2 walks in. To avoid a match, they need a different birthday. 364 out of 365. Person 3. 363 out of 365. Person 4. 362 out of 365. And so on. Each new person has 1 fewer available day. The probability that all n people have different birthdays is 365 over 365 times 364 over 365 times 363 over 365, all the way down to 365 minus n plus 1 over 365. For 23 people, this product equals 0.493. The probability that nobody shares a birthday is 49.3%. So the probability that at least 1 pair does share a birthday is 1 minus that, 50.7%. There it is, 23 people. More likely than not. But why? Where does the intuition fail? Here is the key. You are not checking whether a specific person shares your birthday. You are checking every possible pair, and the number of pairs grows much faster than the number of people. With 23 people, how many unique pairs can you form? The answer is 23 choose 2. 23 times 22 divided by 2. That is 253 pairs. 253 chances for a match. This is the engine of the paradox. You think you are asking about 23 events. You are actually asking about 253 events. The number of comparisons is quadratic in the number of people. With 5 people, you get 10 pairs. With 10 people, 45 pairs. With 23 people, 253 pairs. With 50 people, 1,225 pairs. The number of pairs grows like n squared over 2. Your brain thinks linearly. The math thinks quadratically. Let me show you what this looks like. I will plot the probability of a shared birthday as a function of the number of people. At 10 people, the probability is about 12%. At 20 people, 41%. At 23, it crosses 50. At 30, it is 70%. At 40, 89%. At 50, 97%. At 60, 99.4. By 70, it is 99.9. The curve is not linear, it is not even close. It rises slowly at first, then accelerates through the middle range, then flattens as it approaches 100%. It is an S-curve driven by the quadratic growth of pairs. Let me give you an approximation that makes this even clearer. For small n relative to 365, the probability of at least one shared birthday is approximately 1 minus e to the negative n times n minus 1 over 730. The exponent is negative n squared over 730, roughly. That is the quadratic term doing all the work. When n is 23, the exponent is approximately negative 23 times 22 over 730, which is negative 0.703. E to the negative 0.703 is about 0.495. 1 minus that is 0.505. Very close to the exact answer. This approximation reveals the deep structure. The probability depends on n squared, not n. Double the people, quadruple the exponent. That is why the curve rises so fast. Now I want to show you something that makes this intuitive. Forget the math for a moment. Think of it as a collision problem. Imagine you are throwing balls into 365 buckets. Each ball lands in a random bucket. How many balls do you need to throw before 2 of them land in the same bucket? If you had 365 buckets and threw 366 balls, you would be guaranteed a collision by the pigeonhole principle. But the birthday paradox says you get a 50% chance with just 23 balls. That is roughly the square root of 365. This is a general principle. If you have d possible outcomes and you sample randomly, you expect a collision after roughly the square root of d samples. For 365 days, the square root is 19.1. The exact 50% crossover is at 23, a bit higher because we need a full 50%, not just the expected first collision. This square root rule shows up everywhere. In computer science, it is called the birthday attack. If a hash function has d possible outputs, an attacker only needs to compute roughly the square root of d hashes before finding 2 inputs that produce the same hash. A hash with 128 bits of output has 340 times 10 to the 36th power possible values. Sounds impossibly large, but the birthday attack only needs about 18 times 10 to the 18th power attempts. That is why modern hash functions use 256 bits. They need the security margin to be the square root of a number so large that even the square root is untouchable. The birthday paradox also appears in DNA forensics. A DNA profile that matches 1 in a million sounds airtight. But if you search a database of 100,000 profiles for any match against any other profile, you are making nearly 5 billion comparisons. The expected number of false matches is not 1 in a million, it is about 5,000. In epidemiology, the paradox explains why clusters of rare diseases appear in small towns more often than you expect. If a disease affects 1 in 10,000 people and a town has 500 people, you do not expect any cases. But if you check 10,000 towns, the chance of finding at least one town with 2 or more cases is very high. Not because the disease is clustering, because you are making an enormous number of pairwise comparisons across all towns. Let me take you back to the original problem and make it visual. I am going to simulate the birthday paradox. I will randomly assign birthdays to people entering a room, one at a time, and track when the first collision occurs. Run this 1,000 times. The average first collision happens at about 24 people. The median is at 23. The distribution peaks sharply in the low 20s and has a long, thin tail extending toward the 60s and 70s. Most of the time, the collision happens between person 20 and person 30. Occasionally, it happens at person 10, almost never past 50. Here is what surprises most people. Even knowing the math, even understanding the quadratic growth of pairs, The number 23 still feels too small. You hear the explanation, you follow every step, and some part of your brain still whispers no, it should be higher. And that emotional resistance, that stubborn disbelief in the face of proof, is the real lesson of the birthday paradox. Your brain has an intuition pump for probability, and it is broken. It defaults to linear thinking. It asks, how does 23 compare to 365? And the answer to that question is about 6%. But the right question is, how does 253 compare to 365? And when you phrase it that way, 50% does not feel surprising at all. The birthday paradox is not really about birthdays. It is about the gap between how you count and how combinations grow. It is about the difference between n and n squared. And that gap is hiding in every system where random things collide, in your passwords, in your cryptographic keys, in your genetics, in your satellite communications, in your Monte Carlo simulations. Everywhere random things meet, the square root law is waiting. The moment you have random elements landing in a finite space, collisions arrive far sooner than anyone expects. And this is not just a curiosity. Getting this wrong has real consequences. A cryptographer who ignores the birthday bound builds a system that breaks in the square root of the time they predicted. A forensic analyst who ignores it sends innocent people to prison. A software engineer who ignores it ships a hash table that collapses under half the load it was designed for. The birthday paradox is the universe reminding you that your intuition was built for a world of small numbers and linear relationships, and the real world is neither small nor linear. 23 people, 253 pairs, 50.7%. The math is simple, the intuition is not, and that is exactly why it matters.